Hello, my name is Jerry Johnson. We want to try to get started with this next session.
Hello, my name's Jerry Johnson. We'd like to get started with this next session. So this session is of the moon, geology and regolith. So that's what we should be interested in here. I'm co-chairing this session with Jeff Plessia, who's sitting here. And we've been instructed to keep quite close time because of the parallel sessions. So I'll give a 5-minute warning and a 2-minute warning and then stand up and interrupt if they're not finished by then. Our first speaker is Teemu Ohmann, and he'll be speaking on impact melt-rich lithologies of lunar crater Kepler. Thank you.
Thank you. Yeah, as you've heard during these couple of days, impacts are important, and the National Research Council report also realized that impacts are important. And impact melts in particular are very useful for trying to solve various problems like the bombardment history. If you have melts, you can date them and you can try to figure out. Okay, I can do that. And from melts, you can also try to get the projectiles that created the craters. Therefore, we've been looking at the distribution, volume and properties of impact melt-rich lithologies, particularly in Kepler. And Kepler was noticed to be an interesting possible exploration site already in the 60s and later on for the LRO targeting. And one of the reasons why we've looked at Kepler is that very little photogeologic work has been done before, so essentially everything we do is new. And what we've started to do just recently is to compare photogeology with spectroscopy. This is to give you just a quick background on Kepler. It's located on the near side between Procellarum and Mare Insularum. It overlies Imbrium ejecta, the Alps formation. Stratigraphically, it's younger than Copernicus, but older than Aristarchus. And the location means that it's within the Procellarum crypterrane. And therefore, it excavated high thorium and moderately high iron material beneath the high iron mare. And based on Clementine data, the rim composition is supposed to be noritic. This is just to give you the regional view. This is the Clementine UV vis, Clementine topography, and as you can see from the thorium and iron maps, Kepler is really in the heart of PKT. In this map, Kepler is this orange, pink dot there, and essentially, from volcanic point of view, the youngest lunar basalts are in the area between Kepler and Aristarchus, and there's really some pretty old basalts from 3.57 to younger 1.85 and down to 1.2 if you go a bit further. So there's plenty of volcanic things going on, and it's interesting that possibly there's also a big shield volcano on top of which Kepler impact occurred. This is just a beautiful Apollo 12 oblique view into Kepler. You can see the central uplift complex and the rim terraces there. We've obviously used the beautiful LROC images, NAX and WAX, and the LOLA data, but what we've done is we've integrated that into essentially all image datasets that are available. And as I mentioned, we've just started to use the M-cubed data for spectral stuff. So how do we know if what we claim to be melt is really melt? Well, this is pretty old stuff dating from the late 60s. Melt is supposed to be smooth, and it's generally level surface. It's filling depressions, and usually it has a fairly low albedo, and it's cracked on the surface. And when you have nice flows, you can see levees and various other flow features. This is the only geologic map of the Kepler area. The purple stuff is obviously the Mare, blue is the Alpes formation, meaning Imbrium ejecta. If you zoom into the crater, you can see that there's not really much detail. There's only crater flow material and then crater slope and crater rim material. So this is what the old map looked like, and this is what we came up with. I'm focusing on the melt-rich units, which are smooth floor, mainly on the northern and western parts of the crater, hummocky floor, which covers the rest of the crater floor, terrace sponge, these blue dots, wall lobes, which I'll show you later on, but it's a distinct morphologic feature on the upper crater wall. Rim veneer covers most of the rim crest, and then there's exterior ponge, and you should note that they are heavily concentrated on the northern and northwestern sides of the crater. We'll also briefly look at the melt core units, central uplift, terrace zone, massive slumps, more or less exposed wall, and yeah, I don't think we'll look at the ejecta too much. This is Kaguya image, and you can see the dark smooth floor and hummocky floor here in the southern part. If you look at them a bit closer, it really is smooth, and you have these typical fractures there. It's distinctly different from the hummocky floor on the southern side of the crater floor. These bright hummocks have sizes from tens of meters to kilometers, and if you have stereo data, you can see that there's also longer wavelength irregularities on the hummocky floor, so they are distinctly different. But the material between the hummocks is probably very similar melt-rich material, similar to the smooth floor material. This is a nice 3D perspective view done with the AIMS stereo pipeline software. You can see the smooth floor here grading into the hummocky floor over here, and what we have is fractures at topographic gradients, and Mark Robinson showed yesterday some deep collapse pits in melt-rich material, and we can see them in Kepler as well. Another perspective view of the southeastern terrace zone. You have these fractured terrace ponge, but what you also see is these narrow grooves coming from the upper terrace zone. These are most likely eroded melt channels. And similar things have been seen in other craters like Aristarchus, and so forth and so on. So there probably was more melt over here, which then drained down from this pool, and then it drained down that way and probably that way too. These are the wall lobes that I mentioned. They are high up in the crater wall, distinct morphology. The crater rim is here and the floor is down that way. So melt from the rim flowed down on the wall and formed these stubby features. They are a few meters thick, and from the thickness and the slope we can get the yield strength, which is about 4 to 5 kilopascals, and that's on the order of Kilauea basalts in Hawaii, and it's also similar to what we see in other lunar craters. Now we are outside the crater, so this box here is this here. On the rim flank you can see, I don't know if you can see it on the back, but this is the rim veneer, typically fractured stuff. It flows down, forming an exterior pond, And this box refers to these two figures. I can't really see it too well from here, but you can probably see that there's a levied flow pointed with these yellow arrows, and that ponded into this exterior melt pond here. And there are also a couple of lobes here, so melt was probably diverted to a local depression there. And also for this we can get the yield strength, which is slightly lower than for the wall lobes, and it matches with the morphology. This flowed on the very shallow slope of maybe 5 degrees compared to 25 degrees of the upper interior crater wall. Another perspective view, this time of the central uplift. This is just a minor peak, and what you can see is that the central uplift material is covered with boulders from tens of meters to hundreds of meters, and that's essential for any exploration efforts you might want to do. What I'm calling massive slumps is these chaotic, really irregular masses of material down the crater wall, and it's interesting that there are nice ponds of melt on top of this material, and this most likely means that the formation of these slumps was pretty early, before the melt solidified, so within a couple of weeks, probably. Yeah, this is just to point out a couple of exterior ponds there. Mark Robinson showed this beautiful layered stuff yesterday. This is on the northwestern corner. What you see is about 100 meters thick exposed layer of material. Our best guess is that it's thin, few meters thick Murray basalt flows, individual flows. And on the upper part, you can also see another layered stuff. This might be also basalt flows, but an interesting option is that it might be overturned flat. You can't really distinguish them at the moment. Just to quickly show you the ray distribution, the point here is that the longest and most prominent rays are on the northwestern and western sides. And this is similar to the exterior pond distribution and also the interior melt distribution. Preliminary M-cube stuff, what we see on the crater wall is that low calcium pyroxene dominates. So this corresponds to the earlier Clementine-based noritic determination of the composition. Floor is distinctly different. This green stuff is high calcium pyroxene material. Central uplift is that has a variable calcium pyroxene signature, and there's more plagioclase, and we assume that that's from more anorthositic source. About the wall material, that's probably a mixture between the basalts and the Imbrium ejecta. That's the best working hypothesis we have at the moment. If we'll quickly look at the southeastern part where you see a lot of this green stuff and compare that to the geologic map, there's plenty of this very thin and actually very uncertain material mapped. But the problem is that if you look at the perspective view again, you have some melt pools which are fairly obvious, but this material really doesn't look like it's melt rich in any way. So we suppose that this is extremely thin cover of melt. Something similar has been reported, for instance, in Aristarchus by a recent paper by Jack Mustard. So probably you can't use just spectroscopy to say where the melt is in significant amounts, because you really can't see melt here where it should be according to M-cube data. Just quickly go through the exploration potential. If you go to Kepler with rover, you can get volcanic units, and you can see 3 kilometers down to PKT, Imprium ejecta, and you can also get some central uplift material. To summarize, melt-rich material is present on the floor, ponds and flows and veneer. Kepler was probably created by an oblique impact from southeast. Yield strengths we get are similar to earlier studies, and what we plan to do in the future is to see if other Copernican craters give more or less similar results or not, and get the melt properties and melt volumes constrained. Yep. Thank you.
In order to keep on schedule, we're not going to be able to take any questions right now, so take those up with him